Spectral theory talks about eigenvalues and eigenvectors of a matrix. But let's first see how we define eigenvalues and eigenvector of a matrix. Imagine we're talking about matrix A, which is n by n matrix. So we have n rows and n columns. If we can find any vector x such that if we multiply matrix A by that vector x, that returns vector x multiplied by a scalar number lambda, we call this vector x to be eigenvector of matrix A, and we call corresponding scalar lambda to be eigenvalues. If we can find such a vector x and its corresponding lambda or eigenvalues, so we call this combination to be eigenvalue and eigenvector of a matrix. But the question is that how we can find such a vectors x. If you look at the equation once more, you can recognize that if I consider x to be 0, that's work for every matrix A, because if I set x to be 0 in this equation, A times 0 would be lambda times 0 for any type of the matrix. That's why we are not interested in finding x equal to 0 vector. That's always present and doesn't give us anything special. So as a result, we define eigenvectors to be non-zero vectors which satisfy such equation here. So we are looking for non-zero x values. But let's see how we can find such a vectors. What I'm going to do is to rearrange the equation here and write it down as lambda times x minus a times x equal to 0. What I did basically, I brought ax to the other side of the equation. Now we can factor out x and we can write down this equation as lambda times I minus a multiplied by x equal to 0. So let's check it. If I multiply x to lambda I, so lambda is a scalar number, I is the identity matrix. We know that identity matrix multiplied by any vector returns that vector back. So I times x would be simply x, and multiplied by lambda generates lambda x. Similarly, a times x generates a second term, so it means that these two are basically equivalent to each other. But if you look at this new form of the equation, lambda I minus a times x equal to 0, you might recognize that if I consider whatever is sitting in the parentheses to be a new matrix B, now we have b times x equal to 0. This equation looks like a homogeneous system of linear equations when matrix B would be the matrix of coefficient and x would be the matrix of variables, and we have basically constants on the other side of the equation to be 0. That's why we have a homogeneous one. Basically, if we are interested to find those x vectors which satisfy such equation, that's enough to solve for solutions of such a homogeneous system of equations. Remember that for the homogeneous system of the equation, we can only have two types of the solution. Either we have a unique solution or we have infinitely many solutions. Because we have the other side of the equation to be 0, there is no way we can have no solution option. So the reason we always have a solution is that we can set x to be 0, and x equal to 0 always satisfies such equation no matter what is a matrix B. That's why we at least have one solution available, which is x equal to 0. So if I have a homogeneous equation with a unique solution, that unique solution should be x equal to 0. And if we have infinitely many solutions, one of the possible solutions should be x equal to 0. However, if you remember, I mentioned earlier that we are not interested on x equal to 0 because that's always present. That's why we call it trivial solution. We are interested to find those vectors which are non-zero and satisfy such an equation. That's why we are looking for a condition at which this equation has infinitely many solutions, and only in this situation we can have non-zero solutions available as well for such an equation. So then I'm looking for infinitely many solutions. The question is that what should be the conditions over the matrix of coefficient B in order to have infinitely many solutions in such equation? Well, we might remember that a matrix would be invertible if its determinant is not equal to 0. Furthermore, if matrix of coefficient is invertible, in that case we know that we have a unique solution available for the system. And if the matrix is not invertible, then we have a non-unique solution. In this case, I'm intentionally looking for infinitely many solutions. It means that that's enough to set the condition over the matrix P to be non-invertible. In that case, the solution would be definitely infinitely many solutions, and that's exactly what we're looking for. Furthermore, in order to have matrix P to be a non-invertible matrix, that's enough to set a determinant to be 0. In this case, it's guaranteed that we have some non-zero solutions available for vector x. That's why I'm going to set determinant of this matrix B, which is basically lambda I minus A, to be equal to 0. And then looking for those lambda values which satisfy such an equation. So far we found that in order to find non-zero solutions for the x, we need to satisfy such equation. So using this equation in the box, we can find all lambdas which generate these conditions, and that gives us the eigenvalues corresponding to matrix A. Imagine now we already know what are the eigenvalues, and then we want to find corresponding eigenvectors of each eigenvalue. Basically, I want to find what is the x corresponding to each of the lambdas we can find from this equation. Well, we can find those x's easily by looking at this homogeneous equation once more. Imagine you already know lambdas. You insert one of the lambdas in this equation, so it means that now the mix of coefficients is completely known. And then you are looking for a solution of this homogeneous equation for a specific lambda. The solutions you get here would be basically the eigenvector for this system. However, notice that we intentionally set the condition over this matrix in order to produce infinitely many solutions. It means that here we're going to have infinite solutions out of the system. The question is that which of them would be the eigenvector we have here? The answer is that basically the eigenvector would be the basic solution of such a homogeneous system. And remember that basic solution is the vector in front of the free parameter we have as a solution of such a homogeneous system of equations. So we have another name for equation in the left box, which gives us the lambdas. If I call lambdas to be x, so I can rewrite that equation as determinant of x times I minus a equal to 0. And if you know the matrix A and try to find this determinant, that gives you an equation in terms of the x. You have to solve for those x values which satisfy this condition, which are eigenvalues of the equation. That's why this equation generates a polynomial in terms of x. That's why we call it as a characteristic polynomial of a matrix A. So CAX means that we have a characteristic polynomial of a matrix A. The solutions or the roots of such a polynomial would be basically eigenvalues of the system. We can have basically same eigenvalues repeating more than once as a solution of such a characteristic polynomial. So we call the number of the times a single lambda appears as a root of the characteristic polynomial to be algebraic multiplicity of that eigenvalue. For example, if we have all the lambdas to be distinct, in that case each lambda appears with algebraic multiplicity of 1. However, if for example we have lambda equal to 2 appears twice as a root of such an equation, in that case algebraic multiplicity of lambda equal to 2 would be equal to 2 because it appears twice. Now let's summarize the procedure we have in order to find eigenvalues and eigenvectors of any matrix given to you systematically. So as I mentioned, in the first step you have to solve determinant of lambda I minus a equal to 0 equation, which is basically characteristic polynomial, and find all lambdas satisfying this equation. That gives you all possible eigenvalues for this matrix. Then we insert lambdas one by one in the equation of lambda I minus a multiplied by x equal to 0, and solve the solutions, basic solution for such a homogeneous equation for the given lambda. That basic solution would be eigenvector corresponding to that lambda. Notice that sometimes we have more than one basic solution for a given lambda. So that happens when lambda has the algebraic multiplicity more than 1. So that's totally fine if we have more than one basic solution associated to a lambda given to us.